To calculate voltage drop in low-voltage distribution networks, several methods can be employed. Firstly, the basic Ohm's law method involves calculating the impedance of the cable per unit length, considering both resistance and reactance. This impedance is then multiplied by the cable's total length to find the overall impedance. Finally, Ohm's law, where voltage drop equals current times impedance, is applied to determine the voltage drop. Secondly, the percentage voltage drop method requires measuring or estimating the voltage at the end of the longest cable feeder. The percentage voltage drop is calculated as a fraction of the nominal voltage, for example, 5%. The nominal voltage is then multiplied by this percentage to obtain the voltage drop. Thirdly, the voltage gradient method involves dividing the total voltage drop by the cable's length to find the voltage gradient. The voltage drop along the cable can then be calculated by multiplying the voltage gradient by the distance from the source. Fourthly, power flow analysis utilizes software tools such as PowerWorld or ETAP to model the distribution network. These tools perform a comprehensive power flow analysis, calculating voltage drops along all lines and cables within the network. Fifthly, impedance measurement involves using an impedance meter to directly measure the cable's impedance. Once the impedance is known, Ohm's law can be applied, as described in the first method, to calculate the voltage drop. Sixthly, conductor resistance and reactance tables provide pre-calculated values for various cable types and sizes. These tables can be consulted to find the resistance and reactance values needed to calculate the impedance and subsequently the voltage drop, again using the principles outlined in the first method. When calculating voltage drop, it is crucial to consider several additional factors. Firstly, the load current and power factor significantly influence voltage drop calculations because different equipment pulls differing amount of amps at differing power factors. Secondly, correction factors should be applied to account for the effects of temperature and aging on cable properties. Elevated temperatures typically increase cable resistance, while aging can degrade insulation and overall performance. Thirdly, it is essential to ensure that the calculated voltage drop remains within acceptable limits. Generally, a voltage drop of 3 to 5% is considered the threshold for proper equipment operation. Exceeding this limit can lead to reduced equipment performance, overheating, and potential damage. The choice of method depends on the complexity of the network and the available tools. Simple networks may only need Ohm's law or percentage methods. Complex networks benefit from power flow analysis. Understanding cable characteristics is key for accurate calculations. Always use updated cable specifications. Measure load current accurately. Power factor affects voltage drop significantly. Software tools like ETAP and PowerWorld automate complex calculations. Regular monitoring ensures voltage drop stays within limits. Consider future load growth when designing networks. Proper cable selection minimizes voltage drop. Grounding practices affect voltage drop indirectly. Regularly inspect cables for signs of aging. Temperature correction is vital for accurate results. Use appropriate safety factors in calculations. Document all calculations and assumptions clearly. Compare different calculation methods for validation. Seek expert advice for complex distribution systems. Pay attention to harmonics as they increase voltage drop. Implement voltage regulation devices if needed. Balance loads across phases to reduce voltage drop. Use larger conductors to minimize voltage drop. Minimize cable lengths to reduce voltage drop. Consider using multiple feeders for large loads. Regularly calibrate measurement instruments. Understanding the network topology is crucial. Account for voltage drop in all network components. Regularly update network models in software tools. Ensure adequate ventilation for cables to prevent overheating. Implement energy-efficient measures to reduce load. Use appropriate surge protection devices. Consider the impact of renewable energy sources. Use high-quality cables for long-lasting performance. Properly terminate cables to minimize resistance. Consider using step voltage regulators. Implement power factor correction measures. Conduct regular maintenance of network equipment. Use appropriate cable management practices. Regularly review and update protection settings. Ensure compliance with relevant standards and regulations. Consider the impact of electric vehicle charging loads. Use appropriate labeling and identification for cables. Implement remote monitoring and control systems. Regularly train personnel on voltage drop calculations. Consider using advanced metering infrastructure. Use appropriate grounding and bonding techniques. Regularly inspect and maintain grounding systems. Consider the impact of distributed generation. Use appropriate surge arresters for equipment protection. Implement voltage optimization techniques. Regularly review and update network design. Consider using smart grid technologies. Use appropriate power quality monitoring equipment. Regularly analyze power quality data. Consider the impact of energy storage systems. Use appropriate harmonic filters if needed. Implement demand response programs. Regularly review and update demand response strategies. Consider the impact of microgrids. Use appropriate islanding and reconnection schemes. Regularly review and update islanding strategies. Consider the impact of electric heating loads. Use appropriate load shedding techniques. Regularly review and update load shedding strategies. Consider the impact of seasonal variations in load. Use appropriate seasonal adjustments in calculations. Regularly review and update seasonal adjustments. Consider the impact of weather events on voltage drop. Use appropriate weather-related adjustments in calculations. Regularly review and update weather-related adjustments. Consider the impact of unplanned outages. Use appropriate outage management strategies. Regularly review and update outage management strategies. Consider the impact of cybersecurity threats. Use appropriate cybersecurity measures. Regularly review and update cybersecurity measures. Consider the impact of regulatory changes. Use appropriate compliance measures. Regularly review and update compliance measures. Consider the impact of technological advancements. Use appropriate technology adoption strategies. Regularly review and update technology adoption strategies. Accurate voltage drop calculations are essential for ensuring the reliable and efficient operation of low-voltage distribution networks. By understanding the various methods and considerations involved, engineers and technicians can effectively manage voltage drop and maintain optimal performance of electrical equipment. Always consult with qualified professionals for specific applications and adhere to all applicable codes and regulations. Remember that voltage drop is cumulative, so consider all segments of the circuit. Proper planning and execution of these calculations will ensure a safe and reliable electrical system.